All right, welcome Algebra 2 class. This is our first week of virtual learning. Hope you guys are doing well, and this will be new and an interesting experience. You should take out your packet, the stuff that I gave you for Algebra 2. We're going to start this week basically going through Chapter 5, which is on polynomials and polynomial functions. We're going to start with 5.1. Which is on properties of exponents. So I want to start off today with kind of a simple problem here. And let's talk about the coronavirus. So the last time I checked, it looks like there's about 3,500 confirmed cases of corona in the United States. And an important number to the spread of the virus is the doubling rate. And so right now, this could change a lot, but the doubling rate looks like to be around 4 days. So every 4 days, if we took this and we multiplied by 2, so that means in 4 days we'd have 7,000 cases. And so let's say we took about, like a month's worth. So let's say we did times 2, let's say times 2 7 times. 4, 5, 6, 7. So that'd be about 28 days if the doubling rate stays the same. Right? So we could take this expression and we could write it as 3,500 times 2. And now since there's 7 2's, we could just simply write this as 2 to the 7th. Right? So we can use some simple basic exponent properties to rewrite this expression. That's kind of what we're doing today. But just out of curiosity, if we were to assume that the doubling rate is every 4 days and that doesn't change, then what is that? Well, it's about 448,000. So if the same rate continued to grow at the same rate, in a month, we'd have about 500,000 confirmed cases. That's completely hypothetical. But let's say, that nothing changed, and that the rate continued to double every 4 days. So if I took this, 3,500 times 2 to the 7th, which was like the first month, and let's say it just happened for like another month with no changes in there. So the doubling rate was 4 days, and we said times another 2 to the 7th, right? Well, then how would this work, right? So exponent properties that we'll see today basically says that 2 to the 7th times 2 to the 7th is, we can add those, it's 2 to the 14th, because we can add the exponents when we multiply powers together, right? So if the doubling rate stayed the same, and hopefully it doesn't, because that's why we're staying home, that's why we're separating ourselves from a lot of people, so that it doesn't spread as fast as it would if we didn't do these measures. But if it stayed the same way, then maybe 2 months down the road, sometime in May, what's 3,500 times 2 to the 14th? Well, that's going to grow. The growth is going to continue to get bigger and bigger and bigger and bigger, and if you calculate that out, that's around 57 million cases, right? So you can kind of see, like, from chapter 2 and chapter 1, when we talked about things that are linear growth, that was much different, because every period of time something was being added or subtracted at a very consistent rate. But when we have exponential growth like this, we're doubling or multiplying every unit of time. So the growth can be a lot greater and a lot faster. But today's lesson is really focused around these exponents and what we can do with them. And so, questions like, what do we do when we multiply exponents together or powers together, right? This kind of effect. Well, we add the exponents when that happens. Or what do we do when we divide? What do we do when we have a power or an exponent that's raised to another exponent? And so those are the basic properties that we are going to be looking at today. So we have these rules that we need to go over. So the first one is the multiplication rule. And so that was kind of like the example that we showed previously. If we are multiplying the same number over and over and over again, we're simply going to add the exponents of the base. So for this rule, we're going to put add exponents of common bases. So, for example, we just saw if we had, a base of 2. So a numerical example would be like 2 to the 5th times 2 to the 10th. Well, that would equal, since they have the same base, 2 again, and then 5 plus 10, so 15. Or if I had more of a variable example, so I could have like x squared times x to the 10th times x cubed. If that's my base of x and I'm multiplying those three things, I could add up those exponents and get x to the 15th. I can add them up again. The next one is dividing. So all we're doing with division is subtracting. So we're going to say to subtract the exponents of common bases. So a numerical example there would be like if I had, 3 to the 15th and I'm dividing it by 3 to the 4th. Well, that's going to equal the same base, but I'm going to take 15 minus 4, and so I'll get 3 to the 11th. Or if I have a variable example, I could have like, b to the 20th times, let's say, c to the 10th divided by, let's say, b to the 9th times c squared. So here's a full expression, right? So if I'm dividing common bases here, I have the b as a base, but I also have the c as a base. So I could do these separately and say, well, this is going to equal b to the 20 minus 9, so I have 11, and then I would have to do c to the 10 minus 2, because they're dividing, and so that would be c to the 8th. The next one we're looking at is power to a power. Power to a power just means we're going to multiply the exponents. This really just means we have a power, and then that power is raised to another exponent, so it's kind of part of another power. So to show that, for a numerical example, we could say 2 to the 5th, but if that was in parentheses, then we could say that's raised to the 10th right there, and that means basically I would have 2 to the 5th times 2 to the 5th times 2 to the 5th, but I would be doing that 10 times. So essentially we're going to be multiplying these exponents right there if we ever have that situation. So this would be 2 to the 50th. Right? And if I have a variable example, let's say I have parentheses and I have x squared, and let's put a little bit more in here. Let's say x squared y cubed, all in parentheses, and let's raise that to the 4th. So now if I have multiple in there, okay, basically I'm going to do this twice. I have x squared, that's going to be raised to the 4th. And so I have this power raised to an exponent of 4, and I'm going to have to multiply those numbers. So I'll get x to the 8th. So I'll have x to the 8th, and then there's another factor inside the parentheses, y cubed raised to the 4th. So we multiply there as well and get y to the 12th. The next one that we're going to look at is negative powers. And so what we're going to say here is if we have a power that has a negative exponent and we take that power and we move it to the denominator, or vice versa, whichever way we move it, we can make that exponent positive. So we'll say here in words, if we move the power to the denominator, that means that the exponent becomes positive. Okay, or it could be vice versa. If the exponent was positive to begin with and we moved it from the numerator to the denominator, then it would just simply change the sign. It would just become the opposite. So what we're talking about here is if I have like 3 to the -1, let's say, 3 raised to a -1, which we may not have seen before. You can think of this whole thing as, well, this expression is divided by 1. Now, if I take that power, 3 to the -1, and I simply move it to the bottom, I can do that as long as I take the exponent and change the sign of the exponent. So this would be the same exact thing as 1 over 3 to the +1. And same thing with, let's say I had x to the -7. Let's say x to the -7 divided by, 5 or something like that. So that's going to equal, if I take this, if I want to make all positive exponents, I could take that and I can move it to the bottom so long as I make the exponent +7 instead of -7. So I can do that. If I move it to the bottom, that 5 will stay here, but the x will become to the +7. Now, what's left on the top? There would simply just be a 1 left on the top. So that's what it would be. All right, so the next one that we're going to look at, it's called negative outside parentheses. And that's a kind of a specific one that we run into when we're doing some of these problems. That's a situation. I'm going to do the example first. So if I have specifically a fraction to start with. So let's say I have x to the 5th divided by, say, y squared. And let's say this fraction right here is raised to the -3. And so you could go ahead and follow the properties above, and you can break this down and use several of these properties to get the answer. This kind of happens so much that what this is going to do here, the fraction inside where we have x to the 5th y squared, if we make both of those negative, basically those will switch positions. The top here is going to go to the bottom, and the bottom here will then go to the top if we switch those exponents. So what this is going to be is if I take those and I swap them, I say y squared is now going to be on the top and x to the 5th is now going to be on the bottom. I can do that as long as I make this whole exponent back here the opposite. So since it's -3, I can make this a +3, and those two expressions are going to be equivalent in this case. Now you could keep going a step further here, and if we wanted to, we could take this 3 right here, and we could raise it to the top, and we could raise it to the bottom. So if we were to fully simplify this expression that we have, we would say this is going to be y to the 2 times 3, which is 6, right? Because we're using that power of a power property back up here. Okay, and then on the bottom we have x to the 5th, but that's also being raised to the 3 because we're going to apply this both to the top and to the bottom. So we would multiply those as well and get x to the 15th here. So as you're going to see throughout this section, we're basically just using these properties, but we're going to be using the problems will get a little bit more complicated where you have to use a bunch of them in one problem. So the negative outside parentheses, I'm just going to show you that example, okay, because that's kind of a common one that you'll see. And you could do it a bunch of ways, but this one seems to be the easiest way to get from point A to point B. The last thing we want to look at is scientific notation. Scientific notation just is a form of writing a number, specifically for writing really, really large numbers, to shrink it down so we don't have to write as many digits, or to write really, really, really small numbers to shrink it down so we don't have to write as many numbers after the decimal point. So scientific notation just looks like this. It's a times, and then you have a power of 10. So you have like some number raised to the 10th. Or wrote that backwards. Times 10 raised to some number. Right? So the a, the first number in there, the rule is the first number has to be greater than or equal to 1 and less than 10. And the b value can be any, it just has to be positive, any positive number. Right? So an example could be if we wrote a large number like 2.75 times 10 to the 52nd. Right? So that would be, if I wrote that out, essentially I would have to write 2.75, and I would just have to start writing out a bunch of zeros here, which I'm not going to do, but I would have to move that decimal place over 52 times. 1, 2, 3, 4, 5, 6, 7, 8, 9, and I would have to write out a lot of zeros. So that's the whole point of scientific notation, is that we don't have to write out each one of those things, but we can write that number in a smaller form.